is 8 hours.
Okay.
Just for up to 8 hours. This is 8 hours. You know, like those are green things that we're doing.
So the way it works is the video records what's on my computer screen and then our voices. So as you watch it at home, you can see like what's on my smartboard and what everything I write. And then you can hear me or hear you. So we're going to talk about chemistry, the chemistry of life. And so this all should have been reviewed, right? Like all of it should have been reviewed. From what you learned in chemistry, you probably learned most of this in physical science too. Whether you remembered or not, it's another story. But hopefully I'll refresh your brain today. So, you need to take notes. I will send the PowerPoint to you after class is over, but you can take notes. Handwritten is the practice. Why do we talk about chemistry and biology? Henry, what do you think? It's what? It's essential. Yes, it is. Why is it essential? Eddie.
Because chemistry is like used basically it makes up us, so like we study biology, which is why chemistry makes up life. So yeah.
Yeah. We're made up of chemicals. In order to understand how living things work, you have to understand how these chemicals interact with each other. Really, most of biology is biochemistry. And a lot of the stuff we do, like basically all semester, this semester, is biochemistry. In order to really understand how DNA replicates and how your cells make ATP, you have to understand the chemistry of it. And so we have to review basic chemistry right now so we can move on and understand all this stuff. So I'm going to overview all the basic things you need to know. Also in bio, don't just think about humans. It's really easy to think about ourselves and how everything affects us. So remember, there's all kinds of other things that are living that make up the planet. We are not the majority occupants of this planet at all. Although we might have a majority of the impact of the occupants of this planet, we are not the most dominant biomass species. So plants, you have to think about bacteria. Like bacteria is on you right now, like on your skin right now. There's some that lives in your intestines right now that makes vitamins for you and actually is good for you. Every time you touch someone, you give them dead skin cells and you also give them bacteria. So, your friends. You have your own personal microbiome. Like, it's sort of like your fingerprint. You have your own microbiome fingerprint. You have a unique set of bacteria that live in and on your body that is different from the person sitting next to you. It's actually really cool. Scientists are working right now to see if they could identify someone based on their microbiome. It's interesting. And there's a lot of new research right now that shows that seasonally your microbiome can change. Based on what you eat, your microbiome will change. And it can actually make you healthy or not so healthy. Every time you take antibiotics, you might be killing some of the bacteria, the good bacteria that live in you. It can be replenished. But anyway, it's cool. So we're not the only things that live on this planet, including this little bug guy who's trying to defend himself against someone poking him right there. So. All right, so what is matter? Like the word matter. Anybody remember? It takes up space and has mass. Perfect, right? Matter is anything that takes up space and has mass. You matter. Not funny at all. Sometimes I think I am, but I'm more of the nerdy funny than the actual funny.
That's coming up.
I don't know. I think Kevin Hart is the real funny. Anyway, sorry. So the smallest chemically unbreakable unit of matter is called an atom. And the different types of atoms are called elements. There's different types of atoms and they're called elements, right? Yeah? Yes? Yes. Okay, an atom, so you can't break this down anymore, that actually can still be considered matter. Now, atoms are made up of what we call subatomic particles, yes? Protons, neutrons, electrons. And even then, those things are made up of things called quarks. I'll learn this stuff.
Yeah.
Up quark, down quark, strange quark. There's all kinds of weird. Don't worry about it. You don't need to know it for this class. Physics is where you talk about quarks and crazy stuff. Anyway, so the biological organization of life, I want to review for a minute. This particular diagram was in chapter 1 of your book, which we are not going to be tested on per se. It's sort of just kind of forget it's there, but this diagram we're going to show you is there. But anyways, we started at the bottom. You did learn this in Bio 1, I believe. Atoms make up things called molecules. We have lots of molecules in our body, right? Molecules are things that will hold together by covalent bonds, like carbohydrates, DNA, RNA. There's all kinds of molecules. But anyway, molecules will combine together to make organelles. Remember what organelles are? What's an example of an organelle? Instead of this.
Like a core.
A chloroplast. Yeah. Good. Yeah. This is an organelle too. The myofibrils are organelles and muscle cells. Yes. Chloroplasts are not in us. We don't have chloroplasts, but they are organelles that are in plants and things that are photosynthetic. Eukaryotes. Ooh, big word. I didn't know what that is. We'll come back to it later. The organelles come like a nucleus, ER, remember that kind of stuff? Mitochondria, smooth ER, rough ER, Golgi. Okay, organelles will combine together to make things called cells. Cells combine together to make tissues. Tissues combine together to make organs. Organs combine together to make organ systems. Organ systems combine together to make organisms, which I'll just leave it here. So this semester in Biology 1, AP Bio, we talk about molecules, we talk about organelles and cells. We don't really talk about organs and organ systems a lot. I'll kind of throw a few of them in here randomly interspersed. We do the excretory system when we talk about diffusion and osmosis. We do the immune system when we talk about, incorporate it when we do viruses. We will do the digestive system, we do enzymes, and we'll do endocrine system and nervous system next semester. But basically we skip most of we don't do any histology. If you took anatomy histology, the study of tissues, we don't do that really at all in here. And we don't do like the integumentary system, your skeletal system, and muscular system. We don't do any of that stuff in here. And then next semester, we'll move on to organisms and how they interact with each other. So populations, community, ecosystem, biomes, we do that when we do ecology stuff. Anyway, what's interesting as you move from one level to the next, like new properties emerge. They're called emergent properties. And we'll get back to that in a little bit. But it's kind of like if you have, different organelles kind of on different desks in here, nucleus somewhere, an ER somewhere, Golgi somewhere, then you all, like by themselves, they're not alive, are they? Like the lowest unit of this organization is what? It's actually considered living. A cell. If you go below that to organelles and to tissues and stuff like that, not tissues, organelles and then molecules, those aren't considered living. Like an oxygen, oxygen gas molecule, O2, is not alive, is it? It's just oxygen gas. So anyway, but you combine different molecules together and to make organelles, you have organelles, but themselves are not alive. If you combine organelles together in a certain way and you make a cell, all of a sudden now that's living. It's called an emergent property, a property that didn't exist when you had all those things by themselves below it. So as you move up this biological organization, you have things called emergent properties come about. Properties that are unique that no doubt exist before that level. Anyway. So elements are the different types of atoms. What's an example of an element? Chlorine, oxygen, hydrogen, nitrogen. There's all kinds, right? There's, I think, 92 naturally occurring elements. And of the 92 naturally occurring elements, 25 of them are absolutely essential for life. 25 elements. So here's a periodic table with a lot of the elements. There are also man-made or non-naturally occurring elements. We did not talk about those ever in here. But anyway, so a lot of the ones that are really important to life are the ones here. The four most important to life are carbon, hydrogen, oxygen, nitrogen. Notice over here it makes up 96.3% of the mass of any organism on the planet. So you are mostly carbon, hydrogen, oxygen, carbon, hydrogen, nitrogen, oxygen. CHON. We also are a lot of calcium, phosphorus, potassium, and sulfur. And we're a little bit of sodium chloride and magnesium. When I was in college, I learned that chunk. I've never forgotten it. But it's basically these 6 right here. Because these down here are not, these are the percentages, these aren't really big. But anyway, this is kind of how I remember it. But, so we're mostly made up of those things right there. There are other elements, however, that are absolutely essential for survival. And if you don't have them, you will develop something called a homeostatic imbalance. Those elements are called trace elements. It's kind of written down here at the bottom, but you need to know what trace elements are. Trace elements are elements that are absolutely essential for life, but not in very large quantities at all. Like really small quantities, less than 0.01%. Examples: boron, chromium, cobalt, copper, fluorine, iodine, which I'm going to talk about in a minute, iron, which I'll also talk about, manganese, tin, zinc, blah, 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 blah. So, I'm going to sidetrack. I said a word that I don't know everybody knows. Homeostasis. Can anybody tell me what that is? Ellery, fine. You talk a lot. I'm glad. I'll keep going. Yeah, homeostasis is the maintenance of a stable internal environment. That's like the definition of homeostasis. Every organism has to maintain homeostasis in order to remain alive. And there's usually a range that things maintain. What's our, like in terms of our normal body temperature, what would it be in Celsius? No, that's cold. Celsius. 37. 37 degrees Celsius is around 98.6 degrees Fahrenheit. It's our normal internal body temperature for humans, right? Most of our enzymes, our proteins, everything's nice and happy and functions the best at that body temperature. Now, our body can withstand a range of body temperatures. It will still be in homeostasis. And we actually have ways to help maintain homeostasis. What happens when you start exercising? What do you start to do? You sweat. Your body temperature actually can increase, so you start sweating to help do what to your body temperature? Try to bring it back down, right? Okay, so that's a way that our body can help maintain homeostasis by sweating. What happens if you start getting too cold? You start to shiver. Why does that keep you warm? You're moving.
So why does like 96 weather outside feel hot if our body is 98?
Humidity.
Yeah, it has to do with, well, a lot of it, you're right. You go out west and there isn't humidity, it doesn't feel hot at all. So most of it has to do with humidity. The reason humidity feels a lot hotter is because you can't, have you ever been out west? Okay. You don't notice you're sweating? Like it can be actually 100 degrees Fahrenheit, it doesn't feel that hot. Because you are sweating, but it evaporates off you like right away. And you don't even notice it. But here, when you start to sweat, what happens to the sweat? It's like stays on you. It doesn't evaporate very quickly, and it's disgusting, right? It makes you feel you cannot essentially cool your body down, so you feel a lot hotter. I'll have to do that. Wait. So what happens at colder body temperatures? Why do you start to shiver? Like, why does that keep you warm? You're moving, so it generates heat. Why does it generate heat?
Because you're using energy.
Has nothing to do with friction.
Like you're burning like sugar?
Yes. How do you move? Like, what's the organelle that's burning the sugar? The organelle.
Oh, it's like
Mitochondria. Oh, yeah. Good. The carbohydrates are the sugars, you're right. So the mitochondria, what are they actually making? ATP. All right. You remember learning in Bio 1 that's called cellular respiration. The conversion of the energy, potential energy in sugar to the potential energy ATP is not 100%. Did you remember? Oh, I'm sidetracked. Stop. When you drive your car, I live in Blackwood, so when I drive my car to school, okay, what's my engine doing to the gasoline? Burning it. How, like what is going on physically in the engine? You might know. Pistons, you know about the kids, they might know about engines.
Yeah.
The fuel is ignited, it burns, the energy is converted from chemical energy to mechanical energy. There's these things called pistons and engine that go up and down, eventually turn the wheel things anyway. Creates a lot of friction in that. That conversion is not 100%. So there's a lot of friction being produced. When I got to school, what happened is I like opened my trunk and touched my engine. It would burn my hand because it's so hot, right? That energy conversion was not 100%. A lot of the energy conversion to use, like the fuel cars, is actually lost as all the heat energy. It's wasted. Same thing in our bodies. When you're converting your energy in your food to ATP, a lot of the energy is actually lost as heat, which helps keep our body warm and helps cool us down when we start to shiver. The point is not to actually shiver, but the point is to make your muscles move so you're generating more heat. Anyway.
So is the whole goosebumps thing as effective?
No, that's a good question. The reason you get goosebumps is an evolutionary sort of relic. Long ago, and when we talk about evolution, when we talk about time frame, okay, we're talking about like hundreds of thousands of years ago. You can't even imagine that in your brain. You can't even imagine the a couple hundred years ago when our country was like founded. Like that was just a couple hundred years ago, much less 100,000 years ago. Like you can't even imagine the amount of time that is. But literally that long ago, our ancestors way back then were covered in hair, like legit like hair, like fully hair, like cat and dog's hair. So anyways, way back then, when their hair would stand up, it would be such a huge amount of body air that's standing up, it would actually generate a huge amount of distance between the outside air and your body. It's like a blanket. But we don't have that much body hair anymore, so it's sort of evolutionary there, but it doesn't do anything for us. Make sense? So no, goosebumps don't.
So like the goosebumps is what like is equivalent to like that hair sticking up.
Yeah.
Except we don't have hair, so it's just the goosebumps.
Yeah.
So like it's not.
Yeah, the goosebumps. I mean, there's these little muscles in your skin called erector pili contract and cause your hair to stand up. Yeah. And it's the same mechanism that happened like thousands upon thousands of years ago. But back then we had a lot more hair, so it actually made this giant, you know.
Wow.
It doesn't do it anymore, so we don't have so much hair. Yeah, Ellie. Well, okay, ask anyone like my husband who shaves his head or is bald. It actually holds heat in a whole lot. It does still. Like he's like, you don't even know, Michelle, like in the winter when it's really cold outside, he gets cold so much faster because he shaves all his hair off. And so it really does help insulate your body. You just don't, it still functions. Anyway, so yeah, it still works. Well, we got to, this is what happens in here, we go off. Anyway, so trace elements are important. And if you don't have them, you can develop what we call homeostatic imbalance. So, remember last week we talked about stem cells in your bone marrow, blah, blah, they make your blood cells, right? This is a red blood cell. Red blood cell's function is to do what? Carry oxygen to all of your body cells. Because your mitochondria need oxygen to make that ATP. Okay, without it, you'll die. So hemoglobin is the protein that is found in your red blood cells. I'm going to show you a diagram of hemoglobin real fast. Whoa. No. It looks weird, I know. Images. Sorry, sounds weird. All right, so this is the picture like everyone sees. Let me look at it. I hope you've seen this image before. If not, here you go. Okay. So this is the hemoglobin molecule. It's made of what we call 4 polypeptide protein and hemoglobin protein. And there's in your red blood cells. Ton of it in here. And in the middle of each one of these hemoglobin subunits is something called a heme group. That heme group, there's iron, an iron atom. Each one of them has to have one, that little red dot. Without the iron, your hemoglobin cannot physically bind oxygen. Without it. The iron is absolutely essential for the binding of oxygen to your hemoglobin. Without it, it won't bind it, and then your red blood cells go around, but they're not carrying enough oxygen, and so you develop something called anemia. You heard of that before? Okay. So anemia is when you're not carrying enough oxygen. Symptoms of anemia include Like you're tired really easily, you get cold really easily. You press on part of your skin that looks white and like the red doesn't come back right away. It stays white for a longer period of time, or you can do it on your nails too. Okay. You can eat a lot of ice. Something called pica is and you crave non-nutritive substances. People that have anemia, iron deficiency anemia, one of their symptoms is they eat ice. They eat a lot of ice. I used to have anemia really bad when I first started teaching, and I would have this giant cup. Actually, I'd go to Chick-fil-A in the morning and get a giant cheese and fill it up with ice. And then when I'd run out of ice, I'd like, seriously, every time I'd run out, I'd send the students to go like get more ice out of like the teacher's ice machine. And then I'd eat ice all day long. I had super bad anemia. Normal hemoglobin level in a grown person is around 12 to 14. Mine was around 6, which is really, really low. I ended up having to get like an iron infusion, like ice. But anyway, so you can see anemia is relatively common in females of y'all's age because you start menstruating and you lose blood that way if you don't have a really good diet and all that stuff. It's just really common. Anyways, that's why when we have the blood drive here, a lot of females are sent back for anemia, especially if they try to come during the middle of one of their menstrual cycles. But that's that. There's different types of anemia, B12 anemia. There's different things that are not just iron deficiency anemia, sorry. But anyway, so this is an example of why a trace element is really important. Another example is iodine. So if you don't have enough iodine in your diet, you can develop something like that. Anybody know what that's called?
Oh, it's like your thyroid is like, it's not, you know what I'm trying to say?
I know.
It's a gourd. No.
Now we're so close.
Isn't a textbook?
A goiter.
Goiter.
Yeah. It's not a goiter.
Hey.
So your thyroid gland hangs out in your neck, and it kind of surrounds your trachea. Looks like a butterfly if you spread it out. It's got 2 lobes to it. And your thyroid gland is important in maintaining your metabolism. It produces a hormone called thyroxine. And in order for it to produce a lot of thyroxine, it needs iodine. If a lot of times in developing countries, where this lady is, I guess, there's not enough iodine, they don't get enough iodine in their diet. What happens is the thyroid gland works really hard to make thyroxine, like really hard, and it works and works and works, and it doesn't make it, and so over time it enlarges, or hypertrophy. It can. Well, in America, we have iodine salt. So you don't even have to worry about it. In most developed countries, they're called as iodine. Have you ever noticed on the salt that iodine? You don't have to worry about it. I really don't know. But I just know we don't have to worry about it because it's in all of our salt, like anywhere. It's not a problem. But anyways, there's other causes of, this is hyperthyroidism. Okay. So in this case, it's because there's not enough iodine like in her diet. You can also get hyperthyroidism for other reasons. And one of those is called Graves' disease and has nothing to do with iodine. It's an autoimmune disorder where your body attacks the thyroid gland. Other symptoms of Graves' disease are this thing called exophthalmos where your eyes look like they're bulging out. Let's see.
You know, Google just makes like the worst images, like.
Yeah, I understand now.
What?
Oh, that's bad. I'll do that.
Yeah, they're just kind of like big and like, anyway.
There's a couple of teachers that look like that.
Well, anyway, okay. Here's just some other pictures. Treatment is you just get iodine in the diet and you can start, if it's not Graves' disease, if it's iodine caused. The thyroid will start working again. The problem is once it gets big like this, it won't go back to normal. So a lot of times surgical removal is necessary to get rid of it, and then you'll just have to take thyroid hormones the rest of your life, like a pill, which a lot of people do. Hypothyroidism is the opposite of hyperthyroid. Hypo is when it's not working well enough. You don't have anything. It's not asymptomatic really, except you're just tired a lot. People with hypothyroidism take thyroid hormones as well. Anyway, so that's the goiter. So that's why trace elements are important. That's a really big one right here. The reason they hurt, like the thyroid itself doesn't hurt, but it pushes on neighboring tissues, stretches your skin, so it can cause pain. It can also push on your trachea, make it harder to breathe. So these people would want to have them removed eventually. So, all right, elements versus compounds. So what's a compound? Does anybody know?
Oh, it's like elements together.
Yeah, two of our elements combined together in a certain way. And this is also where you're going to get things called emergent properties. So let's think about different types of compounds. So hydrogen gas, oxygen gas, nitrogen gas, chlorine gas. Yay. Okay. Nitrogen oxide, water, nitrogen dioxide, carbon dioxide. Yeah, these are all different types of compounds. That's exciting. Questions? This is just basic chemistry, physical science review. Yes. All right, so an element is only composed of one element, like a bar of pure gold or something like that. A compound, two or more elements put together in a certain way. There's different types of compounds. They can be ionically bonded, they can be covalently bonded. So here we go. So here we have is sodium. The element sodium is a metal, and it's highly reactive. I don't think this video works. Let's find one where it works. Sodium. What?
That makes your fingers look like that, too?
Oh, there's other symptoms.
Sodium metal in a pool?
What's this?
Oh, we get that.
Yay! That wasn't that exciting.
On to the pool one.
Oh yeah, sodium and water. They're gonna put that pump on wire.
Well, I'm recording it, and you're so.
Is it really hot or something?
Well, you have wires
Oh, yeah.
stuff on your hands. Who are these people and what are they doing? What?
We are recording.
How did they get so much? This is sodium? Why aren't they on the FBI watch?
Hey, don't try this at home, kids. I don't know who these people are or what they're doing.
I feel like they're running.
That's fine.
I have done it.
It's fine.
How can anybody just do this at home?
Hey, they're in a pond, so it's obviously not their home.
Oh wow.
Do you think they were like, oh, that was that
Who are these people? Oh. Oh my gosh. Wow. Alright. Anyway, highly reactive. This stuff is. Chlorine gas here. You can, accidentally make it in your house when you're cleaning with bleach. It says on the bleach bottle, like, do not mix with other cleaners. Because sometimes when you do, it can actually cause this reaction when you make the chlorine gas emit. It can kill you. Chlorine gas is highly toxic and will kill you. Anyways, there we go. So by themselves, these two things are like totally dangerous for different reasons. But you put them together in a certain way, and you have sodium chloride, which is the salt that's Totally not harmful towards you.
Isn't chlorine a trace element though?
Yes, but usually you would get it like, it's not chlorine gas. Chlorine gas is Cl2. Okay, so like Cl negative is usually how we get it. We don't, yeah. Anyway, so yes, it is. Please have. Salt by itself is good for you, sort of. I mean, you don't want too much of it. It can contribute to hypertension, which is high blood pressure. But anyway, there we go. Emergent properties. Moving on. All right, so let's move on. This guy, Mr. Bohr, Dr. Bohr, made up the Bohr model, which you learn in chemistry, I believe, of how atoms are organized with their subatomic particles. So atoms are made up of protons, neutrons, and electrons. Yeah? Remember all this stuff? Protons and neutrons are in the nucleus, and the electrons hang out around the nucleus in what we call an electron cloud. The better way to draw the model would be this, because it really is like a cloud. These electrons are flying around the nucleus at really fast speeds, and they're not just at any, like they're not just here. This would go in front of and behind the board and everywhere, and they go really, 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 really fast. And they're always drawn, like if you have two here, completely opposite of each other because they're repelling each other. Because they're both negatively charged, yes? Okay. So I said this is charge and this is negative. What's the charge on a proton?
Positive.
Plus one. What about neutron? There needs neutral, therefore the name neutron. Electrons and plus one. What about the mass of a proton?
1.27 times. Oh no, never mind.
Let's just say one. Atomic mass unit is AMU. What about neutrons? One. What about, here's our AMU. What about electrons? 1 over 2,000. We say, yeah, it's really small. We say the mass of an electron is negligible. It's so small that we don't actually count it when we talk about the atomic mass. Right? Okay. So the atomic mass would be the mass of the proton plus the mass of the neutron. So we don't really talk about the electrons. So how are the electrons held to the nucleus? The charges. Positive plus negative attract, right? So these electrons are held in the nucleus because of these protons in the middle. They're attracting them, yeah? And so they pull them towards the center of the atom. And that's what they're held in. It's called the electromagnetic force, or EM force. Yep. Okay, remember this from chemistry? All right. So how are the protons held together? Protons are positive and actually repel each other, but there's some force in the nucleus called the strong force. You don't need to know it for bio. I just want to mention that they are held there by this little strong force, but it's only held in the nucleus, or only felt actually in the nucleus and nowhere else. I don't know if you talked about that in chemistry or not, but anyway. Moving on. Okay, so electrons, like I said, they're present in around the nucleus, and they're found in these things called shells. Electron shells, right? You know this from chemistry? Okay, this is an oxygen atom, and here's its first shell, here's its second shell. So it only has two cells denoted by these circles. Shells can hold a certain number of electrons, maximum certain number of electrons. The very first electron shell can only hold 2. Everyone after that can hold a maximum of 8. Whether they have that many or not is another story. Oxygen only has 6 electrons in its outermost shell. The outermost shell, by the way, is called its what? Valence, yeah. The valence shell. The number of electrons in the valence shell of any element determines its reactivity. You remember learning about that stuff too? Okay. We'll move on. We'll talk about that in a little bit. Like I said, they move really, really fast, 220 kilometers a second. That's like insanity. And they'll only be in their own shell. They generally won't jump shells, but they can. They're not going to normally. Okay. And I mentioned that. For bio's sake, we really only talk about like 3 cells. We don't talk too much about it after that. Let's see. Which one has higher energy? The first shell or the second cell? The second shell. The further out you go, the more energy the electrons in those cells have. Okay? Random. Nope. Yay. All right. They can jump, like I said, it's called a quantum leap if they do. To move outer, it take energy, you have to put energy in them because it's a higher energy level out here. So they can fall and release energy from like the outer shell to the inner shell. And when they do that, they usually it emits light. The energy is emitted as a photon of light. And we'll actually do that. I'll show it to you. I'll extract chlorophyll from spinach and it's like green water. But anyways, I'll put a black light to it and it'll start to luminesce and like glow pink because the electrons are falling and they give off photons. Cool. Yep. So this picture's in your book, I think. This showing as you go up shell levels, like to the outermost shells, you have to put in energy and they can fall down and then release energy. Anyway, the falling down one is sort of like going down steps. They're losing potential energy. What's potential energy? Yeah. Energy due to, hold on, position. Good. Yeah.
Okay, so how does it fall from like shell 2 to shell 1 and shell 1 to like
That's a good question. It has to do with like basic. Yeah, ask me why that question when you get there. Don't worry about it for this class. Okay. I don't want to take the time and answer it right now. Can anybody answer that?
I mean, if you could answer
Why not?
She would not. Would she?
Yes.
Yeah.
Or she'd give you a video that would answer it, but you'd have to wait like 30 minutes for the guy to
Like the
actually
last minute it'll answer.
She actually might have gotten it wrong and it might not be on that.
Oh my God, okay. That's a good question, Julia. I feel bad I can't answer
I'm gonna
right
go on YouTube and take it a watch this.
now. How does she not teach? I don't understand.
That's what we're trying to figure out also.
She's not teaching in any other class.
Because chemistry is to weed out those that she doesn't think can actually take AP Chem.
Yeah, so even
I know that.
Chem 1.
And you can go.
Like, she taught all of like 3 things last year, I swear.
I think she had one part.
Yeah, I hate you. It's bird.
I mean, one of the groups got to blow up a balloon that was so well good.
Oh, that was like Chris
I didn't know you were gonna live with that. Bird.
I actually thought that experiment through.
yeah, I know, right? Where's Jean?
I'll ask her to VA. She'll actually be able to answer me. I'll tell you tomorrow.
She right there.
Yeah, but she teaches class. I don't want to bother.
You do it all the time.
We'll have a conversation.
I'm pretty sure she's not.
Now you made me wonder. I'm sorry. Now I'm gonna be like, wait a minute. Because it happens in photosynthesis when the electrons in chlorophyll are actually excited and they jump up to a higher energy state, and then they're captured. I don't know if you learned this in Bio 1. Did you remember that? Like sunlight excites the electrons, they jump, they're captured, and they fall down. Never mind. So that's what I do with the chlorophyll. The electron is like you put the black light on, the electrons will jump to a higher energy level, but then nothing is there to capture it, so it falls back down and emits a photon of light. But it's like, how can it do that if the oxide is full? Like, I can't answer that right now. I don't know. Okay. So, I already talked about that. So, light photons are long, blah, blah, blah. All right, so how big are atoms? How big are atoms?
Really small.
They're teeny, tiny, okay? So 10 to the negative 10 meters is how big, like, this particular atom's, like, shell, from the diameter of the shell. So it's tiny. But if I was going to bring it up to a level that's, like, sort of understandable, if you say the nucleus is the size of a golf ball, let's just say. You can imagine a golf ball, right? If that was the case, if the nucleus is the size of a golf ball, then from the middle of the nucleus to where the first electron shell would be over half a mile away. So in reality, an atom is actually mostly empty space, right? We talk about the whole atom where the electron shells are, it's mostly empty space. So think about it, they're so freaking tiny. How come you're not mostly empty space? They're super tightly packed together. Yeah.
Because you are
Anyway, that's just kind of interesting. Okay. So at the microscopic level, matter is really a lot of empty space, but there's a lot of the things put together, so they're like smashed together. It's cool. You can use big electron microscopes to look at atoms, and you can see them.
Did you see them in college?
No, when I used the big electron microscopes, I was looking at molecules. I didn't use really high-powered ones.
But that was where to see it.
I can show you one later when we do our electron microscope stuff. But I never saw one like myself. Pretty cool. Those machines are super expensive. We'll do this later. Y'all remember Avogadro's number? 6102 times 10 to the 23rd. Right. That's a mole of something, right? A mole, the word mole is sort of analogous to the word dozen. You have a dozen, like, hemoglobins, how many do you have? 12, right? So a mole, if you have a 12 hemoglobins, you have 6.02 times 10 to the 23rd of them. It's just a way to talk about the number. So when we talk about atoms, we have to talk about units, things like the mole, because they're so tiny. We have to use big, big numbers like that. Anyway. Okay, what determines the identity of an atom? What determines it? The number of protons, right? So if you change the number of protons, you change the elements. What happens if you change the number of neutrons? Right, good. Yeah. Okay, so here we have helium and here we have carbon. Helium has 2 protons, 2 neutrons, and 2 electrons. Chemically, this is a stable guy. It's completely inert gas, by the way. Move over here to carbon. Carbon has 6 protons, 6 neutrons, and it has 6 electrons. It has a denser electron shell. It actually has 2 cells and not just one, like helium. Totally different elements, completely different chemical reactivity. Helium has no reactivity. Helium is one of those noble gases where they're super happy and like want everything to leave it alone. Carbon, however, is relatively reactive. We'll talk about that in a little while. Here's our periodic table. We do need to know a little bit about it. So what are these numbers on here? It's 1, 2, 3, 4, 5. That's the atomic number, but what's it telling you? Number of protons, and generally also the number of neutrons. Oh, and electrons. So what are these numbers? The 1.01.
Like all the isotopes.
Yeah. Well, yeah, in reality, it's the average mass of all the isotopes together, right? Well, it's the most commonly occurring one. Anyway, you just need to understand what atomic mass means and how to figure it out. You're not going to have to calculate like the average atomic mass or anything like that. I think you did that in chemistry, didn't you?
Yeah.
Had to figure these numbers out yourself.
Yeah.
Anyways, okay. So in terms of biology, the most important elements we're going to talk about are hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur a little bit. But in terms of chemical reactivity, I want you to keep in mind where hydrogen is and where carbon, nitrogen, oxygen are. Okay. The rest of the stuff on the periodic table we don't need to know much about. Okay. Anyway, I'll come back to this a little bit later. So the number of protons determines its identity. All right. And we know that stuff. And then the atomic mass is how many protons plus neutrons. We know this. Why don't we have the electrons again? They're so tiny, it doesn't matter. Good. We just ignore them. Poor guys. So the charge is when you compare the protons to the electrons. If it's neutral, the charge, like the protons, equals the number of neutrons. Yeah? Yeah? Yeah. Okay. What if you have, down here, if you have 7 electrons and 10 protons, what's your charge? Positive 3. What if you had 10 protons and 12 electrons? Negative 2. You get that kind of stuff? I mean, does that make sense? All right. So here's carbon, atomic number, and then mass number. Yay. So we change the number of protons, we change the element. If we change the number of neutrons, you get isotopes. You're changing the atomic mass, and you can also change the stability. A lot of isotopes are radioactive, and they'll undergo something called radioactive decay, where they can split off neutrinos and split off different things and emit energy in the process. Radioactivity can be harmful. Okay, anytime you go through an X-ray machine, you're getting exposed to some radioactivity. And like, you know, the radioactive bombs were set off in World War II, like Hiroshima, right? And what was some of the fallout from that? People got a lot of cancers and mutations because it changed their DNA. So that would be bad. Obviously, this is why we don't try to use those things. But in small quantities, radiation is not necessarily the worst thing. And it can be used to our advantage a lot in biology and medicine. And I'll give you some examples in a little bit. Okay, so here's carbon, a couple of different isotopes. Carbon 12 and 13 are pretty stable. They don't do much, but carbon 14 is relatively unstable, and it will change over time. So here's carbon 14, and it goes this beta decay, and it becomes nitrogen 14 anyway, so it releases stuff. You can determine some radioactive isotopes decay relatively quickly, and some have a really long lifespan before they'll be completely decayed. It's called their half-life. And you can use radioactive isotopes for something called dating, radiometric dating, where you can determine the age of like rocks. Paleontologists, people kind of use that stuff to determine the average age of fossils and things that they're looking up or they found. You can use different isotopes. You've heard of carbon dating, but there's a lot of other isotopes that can be used besides carbon that have different half-lives, and you can look at rocks that are a whole lot older or much younger. Anyway, okay. So, huh?
How do you get a younger rock?
Well, it's just not as old. Get farther up in the, like when you're digging, you know. The problem is when a lot of people are finding fossils, you know, over time, because the landforms move and like earthquakes and things can shift, the layers, I mean, imagine rock layers, like you cut down, the rock on top will be younger than the rock at the bottom, right? Does that make sense? If you go down and like you dig a hole.
So how do you make new rock?
Well, how do you make a rock? Sedimentary rock, you want me to go over that? Have you heard about sedimentary rock? Sedimentary rock is deposited like at the bottom of like rivers, bodies of water where sediment falls, and over time, like pressure and temperature and all this stuff, it forms rock. That's how it takes a long time. And we're talking about like old stuff, not like hundreds of years old, but like thousands of years old, hundreds of thousands of years old. Anyway, the reason you have to date stuff is because like earthquakes happen, the landforms shift, and so where the layers once used to be in a nice, pretty, like, you know, older, down here, younger, up here, well, if they shift, all of a sudden the layers now are like this. You're not going to know which one was old, which one was younger. So you have to date things. Anyway. So. All right, so how do we use it? We use it a lot in medicine and actually a lot in research now, just basic biological research to look at stuff. So for example, in this particular case, some scientists were interested in looking at, let's say, human cells that were highly mitotic. What does that mean? They're dividing a lot. Highly mitosis is when cells divide, yes? You remember that? Okay, highly mitotic cells are dividing a lot. Okay, so they introduced tritium. Tritium is an isotope of hydrogen, and it's H3. So what does that mean? How many protons and neutrons? If it's hydrogen, it has to have how many protons? Just one. So if it has a mass number of 3, how many neutrons does it have? 2. Good. Okay. So it's an isotope. And they added tritiated thymidine. So the thymidine is made of this tritium with the hydrogen, and added it along with a mixture of some other stuff to these human cells. As they were undergoing, before cells can divide, what do they have to do to their DNA? They have to replicate it or copy it. So they have 2 copies, and they give a copy to each of their daughter cells, right? So during DNA replication, they would have incorporated this radioactive hydrogen, the thymidine, into their new DNA molecules. And so the cells that are dividing the most would incorporate a lot of radioactivity into their DNA molecules. And they were interested in seeing what temperature you incubate these cells at, which one would have the most DNA replication. Okay, and how did they measure it? By using this radioactive isotope. The ones that replicate the more are going to have more radioactivity in them. Does that make sense? So over time, they let it go over, let's say, for 24 hours. And here are the temperatures: 10, 15, 20, 25, 30, 35, 40, 45, 50 degrees Celsius. And here are the test tubes that came from those different cultures. Which one would have the most radioactivity? What do you think? What temperature?
Only 25.
If these are our cells, like what's our normal body temperature? 37 degrees Celsius. So 35 or 41, right? Probably. Why not the 51? It's too hot. If I put you in a 50 degrees Celsius room, I would hurt you. I don't want to do that to you, okay? How about your proteins unravel and I denature you and you die? Okay, what happened if I put you in the freezer? Well, in the refrigerator. Okay, let's not say freezer yet. I'm not going to kill you. Refrigerator. You get really cold. Would you die? No, but what would happen to your chemical reactions? They would slow down, right? Okay. So, which one would probably have the most radioactivity? Around 35 or 40. Here was their graph. Yep, around 35 was the one that had the most. And so we call optimum temperature. Do you remember Bio 1 looking graphs like this for enzyme activity? Okay, we'll do it in here when we do enzymes. Anyway, so my point in all this is they can use radioactive molecules and atoms to study selective in biology. They do it all the time. Basic research. Well, if you don't understand this concept, don't worry about it. We'll talk about it later. Anyway, all right, so here's an image where in a patient, they introduced radioactive glucose into their body. They put radioactive glucose into them. What kinds of cells in your body are going to use a lot of glucose? Muscle cells, more than that. Your body cells. We just talked about mitosis. Cells that are dividing a whole lot, really rapidly. Cancer cells.
Oh, wow.
Why would cancer cells use a whole lot of glucose?
Because they're rapidly.
They're rapidly dividing, like much faster than any other cell in your body. Super rapidly dividing. Cells that are rapidly dividing like that need a lot of glucose. A lot. So in people that have potential symptoms of tumors, cancerous tumors, they can do something like a PET scan on them, PET, positron emission tomography scan. They introduce a radioactive tracer, in this case, the glucose into their body. They let it be in them for an hour or two, and then they put him into a CAT scan machine, this little guy. And what they found on this person is this bright spot. This is where that glucose, the radioactivity is it's a hot spot. So this radioactive glucose is being used in these particular cells, and that's indicative of a tumor. And that's the cells that are rapidly dividing. This is how they can diagnose or find tumors in people's bodies, using this radioactive tracer. That makes sense? They use this a lot in medicine to do stuff like this. Anyway. So radioactive stuff isn't necessarily bad. If you get too much of it, it can actually damage your DNA and can cause cancer. But in small quantities, it's not terrible. It's actually medically useful. So, okay, moving on. All right. What if we change the number of electrons? What will we do to an element? Change its charge, and therefore maybe even change its reactivity a little bit. Okay. We're going to kind of move on. Can you answer this? How many protons are in this guy? 7. It's okay. How many neutrons? 8. How do you know? Because this is the mass number, right? Remember this stuff? Okay. Your first test will be probably not either September 8th or the following Monday, by the way. It's going to be on chapters 2, 3, and 4. Just throwing that out there for you. This kind of stuff will be on there. Okay, I'll try to give you a quiz on that beforehand sometime next week. Just giving your brain a heads up. Okay. How many electrons is in here? 7. Should be the same number of protons, right? Yeah? Okay, good. We're not going to do that. Okay. So let's move into our reactivity. I want to finish as much as I can today. All right. So what determines the reactivity of any particular element is how many electrons are in its valence. I already said there's some outermost shell. And so they can differ. Hydrogen only has 1 in its valence. Carbon has 4. Nitrogen has 5. Oxygen has 6. And so depending, they will have different reactivities. So atoms are the happiest when their valence has 8 or 2. If it's helium, right? Think about those noble gases, the one on the far right. They're like the happiest elements because their valences are completely full. They're just hanging out. Nothing can bother them. They're happiest. Okay? Sorry. So sodium, is this guy happy? He's got like a hot potato. He really wants to get rid of his electron. He only has 1. So he's going to. Most of the time, atoms or elements that only have 1 electron in their valence, they're just going to get rid of it. Like, throw it away. It's a whole lot easier to get rid of 1 than to get 7 more, right? So it's going to get rid of it. So to be the most stable, and I say happy, but it would get rid of it. And it becomes Na what? We got rid of it. What would the charge be?
Na plus 1.
Plus 1, yeah. So what is this now called? A cation, or an ion, and a positively charged ion is called a cation. The terms we know? All right, we should know. Good. Good. Okay, so generally sodium or anything that is in that very first column gives away the electron. Except for hydrogen. What does hydrogen do? Hydrogen does a lot of sharing. We'll talk about that later. All right, chlorine, look at this guy. It's got 1, 2, 3, 4, 5, 6, 7. Is it want to get rid of all 7?
No.
It would just rather do what?
Grab 1.
Get 1 more. Okay, so imagine chlorine gets another little electron. What does it become?
Cl negative.
And so that is called a
Anion.
negatively charged ion is an anion. Good. So anything right around where chlorine is in the periodic table has a tendency to just get 1 more electron or grab it. And when you put 2 elements like these together, what happens? Chlorine generally like rips that electron off of the sodium. Like literally, they'll fly over there. And but it comes off, and all of a sudden we have, because chlorine has a much higher affinity for it, it's going to pull it away. And the bond we now have between, well, now we have a cation and an anion, and these 2 guys attract to each other. So we form something called an ionic bond, right? Remember all this stuff? An ionic bond. They're both happy, and they're not sharing their electrons. One literally took it from the other one. Yeah? So now this guy has like a full valence, and this guy has a full valence, and they're just super happy. And the positive and negative attraction, they're just in this nice little relationship. Good. Ionic bonds form salt crystals. They form something called a crystalline lattice. Something like this. It's a regular arrangement of these atoms. Here's the crystal. Ionic bonds are important in biology because they hold something together. It also is important in the structure of proteins. When we talked about the way things work in water, it's also important. So, anything that's held together with an ionic bond is generally called a salt. Sodium chloride, potassium chloride, magnesium chloride, manganese chloride, calcium carbonate, all this kind of stuff has a general crystalline lattice structure and will form salt crystals. You know about ionic bonds. Okay. Now we move into the stuff that's super important, which is covalent bonds. So the other way atoms can fill their outer shells is not by giving or receiving completely away, but it's by sharing. And sharing is caring, right? So we put 2 hydrogen atoms together by themselves. They just have 1 electron. They just want 1 more. They don't really want to give up their electrons. So what they tend to do is to share. Okay? When you put these 2 hydrogen atoms together, they share their electrons. What happens now, this particular situation, this is called a covalent bond. And a covalent bond is when 2 atoms share a pair of electrons. In this case, this is a single covalent bond. Each one is basically saying, here's my electron. The other one's like, here's my electron. And they're both sharing their electrons. What that means is that, like, by itself, this hydrogen atom, this electron is flying around this guy. This one is flying around here, but they share, their electrons now are flying around both of their shells. An equal amount. Well, in this case, equal amount. Yeah.
Is it possible for an atom to have no electrons?
Then it's just, I don't. No.
It's a black.
Dr. B. I mean, you can. I feel like, what would it, I mean, yeah. It's much more like if anything was going to do that, it'd be hydrogen, but I don't know, like, what it would be. What would it be? Would it just be a proton and a neutron? Like
that a thing?
no. No. I don't know. These things I'll talk about Dr. B. Dr. Wyatt's not here. So just, yeah. All right. Single covalent bond. One pair of sharing. It's always going to be really particular what type of covalent bond it's a. Single. They're sharing equally. Non-polar. It's okay. We'll get to that in a little bit. But if you wanted a review, it's non-polar. Anyway. Okay. They're sharing. This is like my children. Well, my children are always polar covalent bonds. They're never non-polar. Anyway. Yeah. Anyway, okay. So they're just sharing equally. The electrons fly around the nucleus equal amounts of time in either case. And it's actually because they have the same electronegativity. Oh, bless. Do we need to talk about that? Probably. Let's go back. We need to review electronegativity really fast. All right. Y'all remember what electronegativity is? What? Say it again.
The affinity to take electrons.
The affinity an element has towards electrons. Yes. Yes. What is the most electronegative element? Fluorine. It is. Yeah. Fluorine is the most electronegative element on the periodic table. Period. Yes. Fluorine does not occur in biology, so we don't care about it in here. So, of the ones that matter in biology, what's the most electronegative element for biology? Well, no. It's too low. It's right next to it. No, it's too low. Oxygen, yeah. You said it, yeah, oxygen. Now let me talk about what electronegativity is. Let's think about it. So, what happens as we go from left to right in terms of number of electrons, or number of protons, really? They increase, okay? So there's more protons over here than there are over there. Now think about the number of shells. As we go down, what happens with the number of shells? You add another shell every time you go down a row. So down here, what is the attraction of the protons in the nucleus to the electrons in the outermost shell compared to up here? Which one has a greater attraction? Fluorine. Because the shell is much closer to the nucleus. The trend, remember in chemistry you talk about the trends in the periodic table? The electronegativity, the trend is that as you go from left to right and as you go from top to bottom, electronegativity increases. Which is why fluorine is the most electronegative. Because it doesn't have very many shells and it has a lot of protons. Okay, we don't care about the noble gases because they're happy and completely non-reactive. We don't care about them. But for bio, we don't care about fluorine because it doesn't exist. So oxygen is super electronegative. What that means is that oxygen atoms pull electrons towards it a lot. Okay? Okay. So that's over there. Now we got to go back to covalent bonds. All right. There's two types of covalent bonds, and I'm going to talk about it after you draw these pictures. Can you draw these? Don't draw or draw both. And. Remember?
Oh, next up. Well, no, I didn't. But you just rotate mine and it'll look like that.
Draw like this.
I do forget that.
Yeah. There's CH4, that's called methane gas. Carbon and hydrogen, their electronegativity are relatively the same. They have relatively the same attraction to those electrons. So when they're sharing them over here in methane gas, those electrons in those shared partnerships are spending equal amounts of time around the carbon as they are around the hydrogen. The types of bonds that hold together methane gas are called nonpolar covalent bonds. Equal sharing of electrons, and it has to do with the atoms or the elements in that partnership have relatively the same electronegativity. Yeah, I'm trying to show the electrons that are being shared. The red dots are supposed to be from the electrons from carbon, and the blue dots are supposed to be from the hydrogen. Well, that's weird.
And you got that form for the carbon based off of the power medicine? Like the 1, 2, and then you skip the 3, blue, like whatever.
Wait, what's this for?
No, okay, so like when you do the electron of carbon.
Because, yeah, carbon has 4
2,
electrons.
3, 4. Okay. Okay.
I mean, yeah. But you can count how many electrons carbon has in its valence site. It's like the fourth one over.
Yeah.
I just know it because I've been doing this forever. But, okay, now what about water? There we go. What about the electronegativity differences between oxygen and hydrogen? Are they the same or are they different? They're really different. Oxygen is way more electronegative than hydrogen. So what happens, well, so the type of bond here is an unequal sharing. Because oxygen is super electronegative, it's like a big brother versus like a little brother. He's going to take the toy more of the time. So the electrons are going to be spending more of their time around the oxygen shell than they are around the hydrogen. At any given time, most likely the electrons are going to be hanging around the oxygen and not the hydrogen. Does that make sense? That's called our polar covalent bond. Yeah. The blue dots are the electron, like this little dot is this electron, this hydrogen sharing with the oxygen. And this little blue dot is supposed to be the electron, this hydrogen is sharing with that oxygen. Okay? The reason it's called polar is because when this happens, we induce something called dipole on this molecule. And it's because this oxygen, it's like it has 2 extra electrons more of the time. We have induced charges, and they're induced negative charges. It's like it gained 2 electrons. And because this little hydrogen, the oxygen is stealing its electron most of the time, it's like it lost its electron. So it has an induced positive charge. Same thing with this little guy. These are now poles. Part of this molecule is negatively charged, sort of. It's called partial charges, and part of it's positively charged. So it has poles to it, which is called polar covalent bonds. Do Do y'all remember this stuff? I can't tell if it looks on your face or boredom because you got it or like, oh God, I don't know what you're talking about. Okay.
That was,
The bowl.
yeah, like the little 80 style, or the.
This little thing, that's like a delta sign.
Oh.
Okay, so that's just a sign for an induced charge.
Yeah.
It's not a full charge. It's not like CL negative. It's like a partial, it's called a partial charge. The delta sign, yeah. We'll do this more. We have a whole chapter on water, on the chemistry of water. Anyway, we'll get back to this. Okay. We're doing good. Y'all gonna be ahead of the other class, which is good.
Hey.
Okay. Right. There can be single, double, triple bonds in covalent bond situations. So oxygen gas is actually 2 double bonds. Same thing with nitrogen gas, because they both need not just one being shared, but multiple. Triple bonds are stronger than double bonds. Double bonds are stronger than single bonds. It's just the way it is. So here's some pictures. Here's the methane gas we drew. Here's the water molecule that we drew. This is what we call a space filling model. These lines, it's called the ball and stick model. But the line is supposed to be indicative of a covalent bond. You remember building those in chemistry? We're not going to build those in here, but there you go. You can draw double bonds differently. The lines are kind of overlap. You don't need to worry about that in here, though. All right, you need to know all of these things we're drawing are actually molecules. A molecule is a compound that's held together via a covalent bond. Something you should know. So, a water molecule is a water molecule because it's held together with covalent bonds. Covalent bonds are strong. An ionic compound. No. You are made up of a lot of them. Mostly them. DNA is a molecule.
Your mom is cool.
Okay. All right. Some things you should know. Molecular formula is like C6H12O6. That's the molecular formula for something. Okay. You can have the structural formulas. Later on, we're going to talk about isomers and all kinds of fun stuff. Anyways, this is what we call the skeletal formula. And in this case, wherever there's a point, you assume there's a carbon. Did you learn this in chemistry?
No.
Okay. Wherever there's a point and there's not an O or something else written at the end, you have, and there's no letters, you assume it's a carbon. It's just organic chemistry notation. We're going to see this a lot. You kind of need to know it. So, anyways, I just wanted to kind of show you. A lot of times you might see this. You don't ever see the ball and stick models a whole lot unless you build them. So you really only need to know the difference between like this and this. Okay, these are aspirin. Okay. Why do you think a molecular formula is usually not good enough to tell us what we're talking about? Oh, I just said it a minute ago. The word isomer. Oh gosh, y'all know what isomers are? I used to. Oh,
Sometimes.
okay. Well, I'm just going to pause. We'll learn about isomers in chapter 4. Hold on. Did I lose you? Are y'all done? Come back.
Maybe.
Maybe.
Absolutely. Yeah, we looked at 96.
I know. I told you some days are like this. I'm sorry. All right. I'm going to show you a video really fast because I think it's cool.